coming next? Yes, let's keep moving on, okay? And we'll keep moving on with these H2 and N2 examples. And I'll note that thus far we've come up with ground states that are both sigma terms, okay? So, well, what about multiplicity? Well, the multiplicity means the same thing that it did before, right? It's, we know we've got doublet states, triplet states, and singlet states. Sorry, I'm just trying to find my place in my notes. Here we go. Okay, great. So for example, with H2, without even really going and adding up all of those electrons, right, we do it in the exact same way we did with atoms. What I hope you recognize is H2 has got 2 electrons, right, in the 1 sigma G2, and its ground state, they're paired up. That means it has to be a singlet state, okay? And similarly, nitrogen, if we recall, nitrogen, let's go back and just look at its MO diagram. Right, so nitrogen has everything all paired up as well. Like when we look at all of these electrons, you know, it's a lot more complicated than H2, but they're all singlet states. They're all paired up. Okay, beautiful. So I'm not even going to bother doing the sum of all of the S values as long as I recognize what a singlet state is. Okay, and so let's go ahead and write that down. Remember that it was 1 pi x u2, 1 pi y u2, 2 sigma G2. Okay. So now what about our parity term? Okay. Well, a G times a G is a G. A U times a U is a G. And so we can kind of start to think of this as positive times positive equals positive. Negative times negative equals positive. And a U times a G equals a U. So negative times positive equals negative. So that's where these terms come from. Well, check it out. H2 has got 2 sigma G electrons. G times G is G. So that's a 1 sigma G. Beautiful. And then what about nitrogen? Well, nitrogen, you know, technically it's got a U times a U here, which is a G, and a U times a U here, which is also a G, and a G times a G. So it's also a 1 sigma G. Okay? And so finally, there is one, so we're almost done with these term symbols, but not quite yet. So there's one more special symmetry term, and that's for sigma states only. Okay? And so the way this works for the sigma state, we have to consider that a sigma state can be created by this confluence of pi bonds, right? So when we're talking about something like H2, we have no symmetry things to worry about because it's entirely made up of s orbitals. So if I look at my sigma bond for H2, let's see here, I'm going to just draw the sigma bond, right? Which we know was created from 2 positive s orbitals. Well, if I go, so here is my internuclear axis, right? My symmetry operation that I'm going to go through is this, you know, the center of inversion, right, that we talked about before. And when there's no change in that symmetry, so it's positive the whole way through, then we add an extra positive sign there. Okay, so our full molecular term symbol for H2 is 1 sigma G plus, and as it turns out, all closed shell homonuclear diatoms have this term symbol. Okay, so 1 sigma G plus, that is a good thing to recognize because that means all of our bonding orbitals are closed up. Well, as you might guess, nitrogen is also in that category. Okay, all of its bonding orbitals are occupied, right? The 1 sigma G, the 1 pi, and the 2 sigma G. Those are all filled up. So anytime we have that, we're always going to get a 1 sigma G plus. So how do we get that plus term then for nitrogen?